Hi, this is Finn Burke and Isaac Lawrence. We will be presenting on the Enigma code and kind of its history, and its breaking, and then also on the Imitation game, which is a movie that was made about the Enigma code. And so I'm going to kind of walk you through that first part and talk to you about the Enigma code, and then Isaac will talk to you about the movie and how it portrays the Enigma code and like some things it gets right, some things it gets wrong. So first, the Enigma code is the complex encryption system used by the Germans during World War II to secure their military communications. So basically, it was just the way that the Germans encrypted all of their messages during World War II to prevent the Allied forces from being able to decrypt them and recognize their messages and gain a strategic advantage. And the code was generated by the Enigma machine, which was invented in the early 20th century by, I'm probably going to mess up this name, but by a German named Arthur Scherbius. And he actually invented the machine and marketed it as a commercial encryption device for businesses and governments to secure sensitive communications. But its adoption by the German military kind of transformed it into this powerful tool for wartime cryptography. So now that we've talked a little bit about what the Enigma code actually is and how we got it, I'm going to talk to you about how it works. So the Enigma machine itself was a mechanical device that resembled a typewriter, and you can see a picture of one on the left there. And it consists of a keyboard and a series of rotating discs that were called rotors. There were typically 3 or 4 of those rotors, and then also there was a plug board and a lamp board on the machine. And so basically, when a key was pressed on the keyboard, an electrical signal would pass through the rotors, which would scramble the letter according to whatever settings the machine had at the time. And then the encrypted letter would be displayed on the lamp board and show that message. So however many, whatever the setting was, you would put the decrypted message in, it would go through the rotors and then show up on the lamp board encrypted. And so one of the reasons why this was such a difficult code to crack is because it had the settings were easily changed, and the Germans would change the settings daily. And so this created trillions of possible combination and kind of rendered traditional code breaking methods ineffective. And then also different branches of the German military and government used variations of the Enigma machine, and so they each had their own set of rotors, plug board configurations, and operating procedures. And so each of these variants also added an extra layer of complexity for Allied code breakers, because you couldn't just you couldn't use the same tactics and techniques for all German communications. You had to have separate techniques for the German military versus the German Navy, just as an example, or German Army versus the Navy. And then also, when you broke the Army code, that didn't necessarily mean that you broke the Navy code. So that was just another added layer of why this was so difficult to break. And before we talk about it, how they ended up breaking it, I just want to talk to you guys about and compare the Enigma code with some of the other ciphers. And as you could probably gather from the last slide and that information, the Enigma was a substitution cipher. So I'm going to talk to you about the Caesar and Playfair ciphers, which were two other substitution ciphers that we studied. And just as a refresher, substitution ciphers is just when you have a plain text character that you substitute with a ciphertext character. And so that's kind of like it's like a one-for-one substitution of the plain text to the ciphertext. And each letter in the plain text is it's usually replaced by another letter according to a predetermined rule for the cipher. So, and like, as you can see on the left, that's an example of a Caesar cipher where each letter of the alphabet is being substituted by another letter depending on the rotation number, which in this case was 13. So in terms of, just to kind of talk about the differences between these three ciphers, in terms of complexity, the Caesar cipher is the simplest. It's a very simple substitution cipher that involves just shifting each letter in the plain text by a fixed number of positions. So it only has 25 possible keys, so it's pretty easy to solve through brute force. And that's kind of like, you can see on the left that that's a rotation number 13. So you just shift that, and this is kind of getting into the mechanism, but you just shift the letter in the alphabet 13 spaces. So in the example on the left, an A becomes an N, a B becomes an O, a C becomes a P, and so on and so forth, just by shifting the original text by 13 places. The Playfair cipher is a little more complicated than the Caesar cipher. And as far as its mechanism, it involves using a 5x5 grid of letters, and it omits one less common letter to its Q usually, and then it uses a keyword to generate the encryption key. So, and while it's more complex than the Caesar cipher, we'll see that it is still vulnerable. Finally, the Enigma code is significantly more complex than these. I mean, we mentioned earlier that it had trillions of possible combinations, and Isaac will talk later on in this presentation about how that kind of played out in the breaking of the code. So it's just significantly more complex, and then mechanism-wise, it's also significantly more complex because it involves those rotators, plug boards, the daily changing key settings. So that's kind of how you get that trillions of combinations. And so because the mechanism is complex, that kind of makes it the most secure as well. So you can kind of see how all three of these topics in ciphers relate to each other. Like the more complex, typically the more complex the mechanism, the more complex the cipher, the more secure. So that's why the Caesar cipher is the least secure, the Playfair is a little more secure, and then the Enigma was extremely secure in its time before it was broken, which is what I'm going to talk to you about now and how they broke the code. So this really was an extraordinary feat of cryptanalysis, and it was primarily achieved through the efforts of British mathematician Alan Turing, who is extremely famous not only for this, but for inventing the Turing test, which we talked a little bit about in class this year, and then also his team at Bletchley Park during World War II. And they did it kind of using three different, first, Turing played this key role in developing the Bohm device, which was an electromechanical device designed to automate the process of decrypting Enigma message. And this device was based on earlier Polish designs and was crucial in speeding up the decryption process by rapidly testing possible settings of the Enigma machine. So basically he created a machine that could do what humans had been doing in terms of testing possible settings for the machine. Turing also developed a statistical method known as Bambarismus to aid in breaking the code, and that involved analyzing large volumes of intercepted messages to identify patterns and correlations that could reveal the settings of the Enigma machine. So basically, the cryptanalysis at Bletchley Park exploited known plain text, so portions of the message that they knew, which is kind of what we did when we did our code breaking exercise in class. And Isaac's going to talk a little bit about this more later, but they used weather reports and common phrases to kind of help compare known plain text with encrypted message so that they could deduce the settings for the encryption. And that's really what allowed them to break the code. And that they did break the code really did help turn the tide in the war. They were able to decrypt German communications and gain insights into their plans, troop movements, and strategies, which obviously helped shape the Allied military operations and ultimately contribute to the Allied victory. And Isaac will talk a little bit about that and then the consequences stemming from that as well when he talks about Imitation Game. So I'm going to hand it over to him now.
Yeah, so for the second portion of this project, we watched Imitation Game and compared, how Enigma and Alan Turing and the whole Bletchley Park operation compared in the film to what we now know it was like in real life. So just a little background for anyone who hasn't seen it. The Imitation Game, it came out in 2014. Benedict Cumberbatch was Alan Turing in it. And so kind of it starts off, Turing arrives at Bletchley Park, and there's this team of 5 cryptographers, mostly with backgrounds in math, who are just, manually going through the code every day. And Turing sees this and he's like, this isn't going to work. We need like a way to automate this. But he just kind of gets shut down. So he sends, in the movie, he sends a letter to Winston Churchill and says, like, this is dire. It's not going to happen if things continue the way they're going. Like, put me in charge. And so he gets put in charge. He fires 2 of the cryptographers on the team, and he puts like a test in the newspapers throughout England. And basically, it's just a little code breaking test, and they send them back if they got it right. And so Turing is leading this test at Bletchley Park. They all show up, and he says, like, here's this test. You need to solve it in 6 minutes to be considered for this project. And like, he kind of admits to one of his friends, like, it took me 8 minutes. And this woman, Joan Clark, solves it in like 5.5, around 5 minutes. And she ends up, joining the team and playing a really big part in how Enigma was broken later on. So in the film, the bomb device, which I know its real code name was Victory, it's referred to as Christopher, which is a liberty that was taken in the film. Christopher was the name of a classmate that Turing was fond of. I know that was in real life as well as in the movie, but they took a little bit of liberty with that. And that's something about the movie too, is that they really talk about Turing's personal life and his upbringing, and he was like socially awkward, and he ended up after the war being ostracized for his sexuality, and it talks a lot about that. But just for the scope of our project, thinking about Christopher, Turing, recognizing that there was just too many combinations in any given day to figure out, and the fact that Enigma changed every day compounded that problem. He wanted the machine to be able to think, and so not necessarily just manually try every single combination, because there's no machine at that time that would be able to do that many combinations before the code would change. And so he wanted it to be adaptive and kind of intuitive. And originally the budget was £100,000, which today is about $8 million, which, if you think about it, we're spending billions of dollars on projects. This is really like a pretty low price tag. And part of it was that Turing, like himself, built the machine with his own hands. So the big scene in Imitation Game, the one that I remember from when I saw it back when it came out, was Turing Turing is sitting at a bar, and there's just a group of women who would like analyze or accumulate the like telegrams coming from Germany every day. And she just made a comment about how she thought the guy, the telegraph operator that she was in charge of, kind of monitoring, how she thought he had a girlfriend because he started every telegram with the same 5 letters, Cilly, and she assumed that was like Silly was the name of his girlfriend. And so it kind of clicked in Turing's mind all of a sudden. They were supposed to be a random 5 letters at the start of every message, but it kind of clicked for him that we only need to be searching for based on the ones that we have from this guy, we only need to be searching for certain words that we know are going to be showing up, and so that every day at 6 a.m. Germany and like the armed forces would put out a weather report, and so in every single one they knew that there was going to be 3 words: weather, Heil, and Hitler. That's how it would end. And so Turing runs off from the bar. He goes and punches, rewires the Christopher machine to look only for combinations that had these 3 words, those letters in that order. And basically you see the gears turning for 30 seconds and then it stops and it spits out this cipher. And Turing runs across the street, goes over to the Enigma machine that they have that I think was captured earlier in the war. And changes the codes, puts in the cipher, types in an encrypted message that they have, and it spits out something that they can understand. And so that's kind of like the light bulb moment. They get it. They have it now. They know how to crack these codes every day. And before this, it was the number that they said is if you had 10 men working on cracking Enigma, doing one variation every minute, 24/7, it would take 20 million years for them to try all the possible combinations, and that's without considering that it resets every day. So really, it was impossible, and this not only made it possible, but made it something that they could, crack every day with the new variation. And so this gets cracked. I think there's like 35-40 minutes left in the movie. The rest of it kind of talks about the practical implications. Like right off the bat, there was like a passenger convoy that was going to be targeted by German U-boats, and the code breakers didn't want to use the code and like get air support there because it would tip off the Germans that like they had cracked it. And so kind of just thinking about the practical implications beyond cryptography, like human lives were at stake, and having to kind of save it or use it in really high leverage moments. But that's our presentation. Thank you for listening. This was like a very interesting topic, and hope that it was interesting to listen to as well. Thanks.